We can gain more insight about fluid flow by viewing the energy within. Let's inspect any 2 points in flowing fluid and identify important properties. They are force associated with flow, cross-sectional area, flow velocity, and the elevation of point from datum. First, work is done when fluid flows through a pipe. Work done by a system is a product of the exerted force F and the resultant displacement x. When applying this to our pipe flow case, force can be expressed as the product of pressure P and cross-sectional area of fluid A at one point. Let us process the multiplication of A and x and introduce volume V. The change in work done is expressed as follows. Since the fluid is incompressible, the volume of fluid mass in consideration for both points do not change. Therefore, we can simplify the expression for the change in work done. By the principle of conservation of energy, the change in work done must be balanced by the change in kinetic and potential energy. The kinetic energy, K, is half the product of mass m and square of velocity v. The change in kinetic energy is the difference between the kinetic energy at the point 2 and 1. We can convert the expression knowing the mass is the product of density and volume. Again, the volume remains the same at both points, and the density shall be the same throughout the fluid. Therefore, we have a simplified expression for kinetic energy. On the other hand, the potential energy is a product of mass m and elevation h and then factored by gravitational acceleration g. Again, the quantity mass is expressed as a product of density and volume. Finally, we obtain the simplified version of potential energy expression knowing the volume and density of the inspected points are consistent. The terms for work done, kinetic energy and potential energy are arranged in the way that obeys the principle of conservation of energy. The simplification of the expression involves multiple steps. First, we remove the term V from both sides. Then, we proceed with dividing rho g for all terms on both sides. At this point, terms involving properties for point 1 are placed at the left-hand side, and those for point 2 are on right-hand side. The derived equation consists of pressure head, velocity head, and elevation head. It is known as Bernoulli's equation, and it is applicable to frictionless pipe. When friction is to be considered, head loss needs to be introduced at the right-hand side of the equation. There are two types of head loss, major and minor head loss. Major head loss comes from the friction between the fluid and pipe wall. It can be calculated by using either Darcy-Weisbach equation or Hazer-Williams equation. On the other hand, minor head loss is due to bends and fittings. By adding the pressure head, velocity head, and elevation head at one point, we can determine its total energy. When we do this for all the points along a pipeline, we obtain an energy grade line EGL. The difference between the energy of 2 points is the head loss. The head loss with respect to upstream or the source of fluid such as reservoir is usually concerned. Other than EGL, we also have hydraulic grade line HGL. Hydraulic grade consists of only pressure and elevation heads. It is also known as piezometric head, which visualizes the pressure in fluid due to the heads when we put a piezometer at one point. Let's look at one simple example. The distance between a 5-meter depth reservoir and the supply destination is 200 meters. Bottom water level of reservoir is at 100 meter elevation, while the elevation of the other end is 75 meter. The internal pipe diameter is taken as 500 mm and the design flow rate is 900 liters per second or 0.9 cubic. Hazen-Williams coefficient C is taken as 100. How would the EGL and HGL look like for this system? The pipe end's elevation changes by 25 meters over the plane length of 200 meters. In other words, the elevation changes by 1 meter for every 8 meter length. Let's say we want to determine the heads at every 10 meter interval. The elevation head for these points is easy to determine by using linear interpolation. The pipe flow and pipe geometry remain the same throughout the system. The flow velocity and velocity head should be the same as well. The cross-sectional area of pipe is 0.196 square meter, and therefore, the flow velocity is 4.58 meter per second. The velocity head is 1.07 meter for all the points on the pipeline. For reservoir and supply destination, it should be 0. Next, we proceed with the calculation of head loss. Using Hazen-Williams head loss equation, the head loss gradient of 0.05 meter per meter flow length is obtained. By multiplying the distance in pipe between the points and reservoir, we obtain the cumulative head loss up until those points. The pressure head at the reservoir is taken as 5 meter. Therefore, total head without considering losses for all these points should be 105 meter. By subtracting the elevation head, velocity head, and head loss at the interested points, we obtain the pressure head. By adding the pressure head and elevation head, we obtain piezometric head. On the other hand, by adding piezometric head and velocity head, we obtain the total energy at those points. By joining the piezometric head at all points, we obtain HGL. By joining the total energy at all points, EGL is produced instead. The difference between HGL and EGL is negligible, since the velocity head is too small compared to piezometric head. In water reticulation design, hydraulic grade and pressure head and the destination nodes is concerned to ensure the water supply satisfies consumers' daily usage and firefighting requirements. Thank you for watching. If you find this video helpful, please share it with your friends. We'll see you guys soon. Goodbye.